Hello, welcome back. We are looking at section 7.3, optimizing functions of two variables. In this video, we're going to try to tackle essentially this middle learning objective. We're going to take a look at one kind of chunky word problem and see if we can't apply the strategies of this section to it. Let's get where we're supposed to get. Okay, peanuts. So we're going to try to take this model. We've got a company in Virginia that sells jumbo cashews and a health fusion nut mix. And we're going to make a regression model that says essentially we imagine they're going to sell this many tubs of the cashews and this many tubs, thousands, tins of the health fusion mix when the cashews are X dollars a piece and the tins of health fusion are Y dollars per piece. So you can sort of see that certainly the demand for the cashews goes down as its price increases, and as the health mix gets more expensive, the cashews get a little more popular. And then the reverse is true for the health fusion mix. So our strategy here is to first find the function we're interested in, which is, turns out, revenue, figure out where that would be maximized, and then get an idea of what that maximum revenue actually is. So buckle in. These are always fun. Okay, so we've got some modeling to do first. Remember, if we want revenue from a single product, then we look at price times quantity. If we've got more than one product, then we take a look at price times quantity plus the price times quantity for the other. So the sum of these individual revenues would give us this total revenue. So we know that the price of the this first one was the cashews. The price of the cashews we were calling X. And then its quantity was this linear model that we had claimed would work for us here. And then something very similar but not identical for the cashews. This second price we were calling a variable Y. And the second quantity was that demand equation. Okay, so our revenue formula is going to look like the sum of these two things. And with some distribution, there's only one like term to combine. We end up with an XY term from this and an XY term from that one, and we put them together in the middle. Other than that, all the X's and Y's and X squareds and Y squareds are all their own terms. So now we have the function that we're actually interested in, which is a good start. So we're going to take this and find its critical points. And you might recall that that's going to involve taking each of the two partial derivatives and setting them equal to 0. So revenue with X changing is going to look like the derivative of X. And I'll scroll back here in just a second so we can think about this. But so our revenue looks like, a revenue derivative with respect to X looks like 8 minus 0.25Y minus X. R sub Y has a similar kind of structure. And just to look back and remind ourselves, we're taking the derivative of this expression here. First with respect to X, so we'd have just 8, there's a 0. We'd have a 0.2 times Y, because remember the X term would disappear from the derivative. And then the X squared term is the most interesting thing here, where the 2 would come down and we'd have just minus X. And a similar scenario for finding derivative with respect to Y. So our task is not just to find these derivatives, but in fact to figure out where they might be equal to 0 in this system of equations, these simultaneous equations. So at this point, this y and that y are the same quantity. We just don't know what it is yet. This x and that x are the same quantity. We're just not sure about it yet. So we're going to try to combine these two equations. So there's a bunch of different ways you can solve linear equations. One of the sneaky ones that I thought I would try in this case is basically, since this one is easy to solve for x, just adding x to the other side. What if we solve this one for x as well, and then we'd have two quantities to set equal. So if we solve this set equal to x, that is, we take away 6, we add 0.4, and we divide off this factor of 0.25, this is where we end up. And the advantage to that then is now we have two expressions that are both equal to x. And so that must mean that these things are both equal as well, because these x's are actually the same number. We're not sure what it is yet, but that must mean that these green underlined things are also identical, which is perfect because if we get to combine those, now we have a single equation with one variable, which again is sort of what every system dreams of. So with some quick algebra, we can add the 24 over to get 32. We can subtract this 0.25 to get a 1.35 factor on this y. Divide that out, and lo and behold, we've got ourselves a value for y. Remember, we're not done at this point, though. We're looking for a critical point for this nut sales thing. So we need both an x and a y because our inputs for this function were both x and y. We can go back to either one of there's a whole bunch of different equations. But again, I'll pick one where x is already solved for. We did all this hard work in that previous slide of getting x by itself. Let's make use of it again. So if we're trying to figure out a value for x, we'll pick an equation where x is already solved for it. Save us a little bit of time. So we take this newfound value of y, dump it in, 8 plus 1 1/4 times that is going to give us something around 13.93. So with that in hand, we're going to see the only critical points are here's our x value, 13.93, and y value is 23.7. So we're going to classify this point. And remember, classify means we don't yet know if this critical point is a max or a min or maybe neither. We're hoping, given the framing of this original question, that it will be a maximum, because that would be the most interesting result for us. But we'll make sure, do our due diligence here. So just by way of recollection, our r sub x looked like 8 plus 1/4 y minus x. And the reason that is germane here is that we're going to be taking r sub xx. In other words, starting with this and taking its derivative. Let me stick with green real quick. So taking the derivative of that thing with x as the variable again is just -1. Nothing else has x's in it, so that's going to fall out. If we do the same thing, r sub y, again, just by way of recollection, we did this in a slide ago. And then we've got 0.4y. So taking this expression and taking its derivative with respect to y again, so starting with this, there's no y's there, 0. No y's there, 0. And the derivative of this is the only thing that kind of has anything interesting left. And so this is all what's playing out here. So here is our -0.4 term. The -1 that we got is right about here. And then the mixed partial, the r sub xy. So if we started with r sub x and took the derivative of this thing with respect to y, we should expect to get, well, 0 plus, this actually has a y on it, so a derivative of there would be 0.25. And if you're feeling sneaky, again, you could have done this the other direction, r sub y, so take this thing and take its derivative with x as the variable. So there's no variable there, derivative of that is 0.25. There's no x's on this, so derivative of that is 0, but same answer is circled in magenta there, 0.25, which is comforting. It ought to be that way. Okay, so then what actually falls out of this is essentially 0.3375, which I guess more interestingly is a positive number. That's basically all we really care about that. So that dumps us into this more interesting scenario where we have to consider it's a max or a min. So we know for sure it's not a saddle point. That's basically the only clarity we've got on it at this point. So the last thing to check is, great, this d thing is positive. So now we go back and look at our rxx or ryy. Again, I made the claim that in the previous video that it doesn't actually matter if we look at rxx or ryy, because if one's positive, the other will be positive in this scenario. That's the only way for us to end up with this d thing being positive, is if these guys are the same sign. So, but just because it's easier to pick something and go with it, r sub xx is -1. So clearly that satisfies this less than 0 target. And great, what we do have is actually a maximum. So this is more comfort than any real new information for us, because the hope was, starting with this revenue function, that whatever critical point we come up with is that going to correspond to a maximum. So this is more of a sigh of relief than a, oh, that's interesting kind of moment. So the last thing they wanted was the actual maximum revenue, like how much money do they make out of this? So if we take that x coordinate and y coordinate and dump those in here, R of that is something around 126 and some change. So just keeping track of units, you might recall that while X was in dollars and Y was in dollars, the demand was actually in thousands. So if you multiply those things together, that's how revenue works. If we take R and know that that's P times Q, if this is in dollars and this is in thousands of something, thousands of stuff, then the unit on that is going to be, well, so this is dollars per stuff technically. So the units on that are the units on the actual product are going to go away. That amount of the tins of nuts that we sell disappears, but the thousands of dollars is still there. So we still have thousands. So 126 is really 126,000 and some change. So there is an applied instance and our first time in these videos of going through from scratch, starting modeling a formula, finding critical points, classifying them using the second partials test. In the next video, we will consider closed bounded regions that we optimize on.